Hello and welcome to the Build Better Homes podcast. I'm your host, Royal Mortier, and I'm here with my co-host, John O'Shea. How you doing today, John?
I'm doing well. How are you today, Royal?
I'm doing lovely.
Ready to get this show on the road and talk about wood?
We work with it every day. Work with it every day. We might as well talk about it. So, but I do want to give some geography to some people. So we're actually getting quite a few listeners. It's pretty awesome. Thank you for listening with us.
Absolutely.
We try and be entertaining, provide some great topics, but also understand we're coming at this from two very different realms or sides of the United States. So, John, where are you at?
I'm up here in Oregon, a little town called McMinnville right outside of Portland Metro, but basically, the Portland, Oregon area. So West Coast, about an hour and a half away from the actual coastline. We have a house at the beach that we always go to. So we're as far west as you can get in the United States. And, our bread and butter, your ethos of your whole engineering career and my builder career all kind of started on the I-5 corridor. So I'm in that area.
Yep. Very, very familiar with the I-5 corridor and everything that goes along there. And I'm actually all the way on the East Coast. I'm in Florida. I live in a little town called Gulf Breeze. It's a beautiful little peninsula. We're right across the water from Pensacola Beach. The Emerald Coast, as we like to call it, or as other people call it, the Redneck Riviera. So you nice. Go ahead and pick your poison on that one. Gulf Breeze, of course, the most notable thing that has occurred to Gulf Breeze in recent years is this is actually where the Tiger King was arrested.
That's just where is he still alive? Is he still kicking? I know.
Yeah.
There's been like he attempted murder when his wife or she tried to kill him. And
that beat Carol Baskin. Carol Baskin. Yeah.
Wow, did he come on the scene strong a few years ago?
Yeah. Well, we have no kings, but we do have the Tiger King. That's the only king we care to have. So
nice.
Yeah, he was arrested at the hospital, the Baptist hospital in the parking lot, which is actually just down the street from where I live now.
That's hilarious.
Which is hilarious. I feel like they almost need to have a plaque there, like here's where the Tiger King was arrested.
Yeah, every now and then he flares up in the media, like you see he's trying to sue somebody, or he's trying to get out, or he's trying to get a pardon, or I think he had estranged lovers all over the place. I mean, he's an interesting dude, man.
Yeah.
And, I don't know if he's ever going to get out, but what a show that was.
We moved here about 3 years ago, and I actually didn't even watch the Tiger King until after we moved here, which I mean, it had been out for a couple of years. And then we get to the season finale episode and it's like, he's getting arrested in Gulf Breeze. And I'm like,
what?
Like, that's where we live. So yeah, it's pretty funny. It's pretty funny. So anyways, what we're going to kind of do today is we are going to be talking about wood construction, and really what we're going to be talking about is value engineering from the engineering of the home standpoint. So we're going to stay really on the more conventional framing methods, but I started as a home builder and I came to the engineering side, came to the dark side, as you want to call it. And the big reason I did that was obviously I had a passion for residential construction. I mean, I started in it at 15, but I also had a frustration with the engineering that we regularly got. You could take the same home, give it to 3 different engineers, and you'd have 3 different answers. Granted, each engineer has their own way and their approach they can do it, but we have such uniformity now, and with the wood design codes and the materials that we have available, and everything kind of centralizes down to certain manufacturers of certain products, certain materials, and everybody uses the same exact wood design code. What's funny is the American Wood Council and the Canadian Wood Council is the same organization, right? Oh. The other thing that many people don't understand is the majority of wood material that we use in the US actually comes from Canada. And there's 2 reasons for that. One, the environmental regulations that have been implemented in places like the Northwest. Doug fir is still the strongest wood product that we can engineer with. However, Doug fir grows predominantly in the Northwest, and environmental regulations have really caused a lot of cost prohibitiveness in our harvesting and production of Doug fir materials out of the Northwest. But the secondary part of that is, yes, Doug fir is the strongest, but then if you actually dive into the wood design code, there's what's called Doug fir North. And Doug fir North is actually even stronger. It has higher capacities, and Doug fir North refers to specifically Douglas fir that comes out of Canada, our nice people to the north. So the reason that wood is more, they believe it's stronger, more resilient, is just because of the environment it incurs, being in the colder temperatures, the more extreme environments, and the mountainous regions of Canada. So everything, the grain grows a little tighter, so the wood's a little stronger. But then like here, I'm in the Southeast, we use a lot of spruce pine fir and yellow pine, which in itself is a softer wood, a softer material, still fully functional. Just we're going to see often lower design values, which for general wall framing typically isn't a significant point of contention. But when we get into beams and headers and stuff like that, then we obviously have a lower capacity, which then brings us into engineered products and the engineered materials. That's just a quick overview on materials, but really what we want to focus on today is we can start talking about value engineering of how we do that supporting vertical loads, and then we can start with that on how we do it with resisting lateral loads. So vertical would be like your dead load, your live load, your snow loads, and lateral being like your wind loads, your seismic loads, or now we even design for tornado loading, hurricane loading, and stuff like that.
I think one of the keys that I want to key off of, there's Royals really coming from this from a engineering perspective, obviously, right? Value engineering. How can we use the flexibility of not only vertical and horizontal values and how they are intertwined with the strength and the wood fibers and the different types of wood he's mentioning, but I'm coming from it from the home builder side. So I'm looking at, what are the different types of homes that we're going to be engineering? Are they first-time buyers? Are they move-up buyers? Is it a custom home? Is it a really high-end home with large spans? What are we doing with wood, and what can we do with wood from the architectural and design side? So we're going to kind of bounce those two different topics off one another and get into how those two things can be reciprocal, actually, how you can use different materials and also different design techniques to create a really strong value engineering proposition for any given home or design. So, yeah, I just wanted to add that in there.
Yeah, and you bring a great insight into this. From us on the engineering side, and one thing that I think we do that may be different from many is we work with our builders on establishing an SOP, a standard operating procedure for their different levels of builds. What are the different tiers from like the marketing or the builder side? What are the different tiers that are commonly classified as?
We have our first-time home buyer, production build, 1 and 2 story, usually 2,300 square feet, 2,500 square feet or less. They have a library that they put out that basically says, okay, we build these 50 homes and we're going to reuse these plans and we're going to build these in different areas, let's say along the I-5 corridor, Washington and Oregon. Those are generally like first-time home buyer or move-up buyer homes. And then some builders that we have also have a custom home line. Mm-hmm. So those are people that come in with a napkin sketch and they want to take it to concept, get the concept vetted out, which value engineering can play into concepts as well. And then they go into a full set of construction documents. And then there's your high-end customer who already kind of knows what they want, probably already have a concept in their head, maybe a napkin sketch, but maybe they've engaged an online plan firm and they bought a plan that's similar to what they want, and then they want to alter it and make it their own, or maybe they start from nothing, like the napkin sketch. But, those are the different tiers that I see in the home build. Kind of if you want to take it to macro, these are the 3 different classes of what we're looking at. Right.
In residential, and how I've also heard it is like you have your low income, which is, sometimes a lot more rental based.
Yeah.
But, you can almost get into that starter home, that first time home buyer, which, is going to be somewhere we're designing houses. We're working with some builders where that entry level to get into that entry price point that people need in certain areas. I mean, we're getting homes into that 1,200 to 1,400 square foot.
Yeah.
Definitely on the lower side. Townhouses definitely being a great starter point. And then, and we'll have a whole separate episode on townhouses and the building code townhouse exception. That's a great way to flex as a builder. And then, then you get into your first time home buyer, and then you're going into like your second home, maybe a little larger. You're a little more progressed in your income with your company. Maybe you got a couple kids at home, so you need some more space, those kinds of things. And then we get into the mid-level custom, and then into your higher level custom. And I'll explain kind of the divide in those. But from the engineering standpoint, we set up an SOP with it. We have some builders that build everywhere from that entry level all the way up to the high end custom. And we work with that builder, and for the vertical loading, it's a different SOP for each. And what I mean by that is our entry level homes tend to be smaller openings. And we're also trying to cut cost anywhere we can, because that cost of construction, increased cost of construction, gets passed on to the buyer.
Yeah.
And so what we're looking at standard headers that are going to be the least expensive. And the builder will adjust window sizes, adjust floor framing, adjust overall width and depth of the building to try and cut down the cost of construction, not so much just the square footage. We can get, I can take a home that's 1,400 square feet and lay it out two different ways, and the engineering or the cost of materials can be substantially more in one configuration versus the other.
Yeah, I mean, but builders want to standardize things. They want to put 2 3.0 by 4.0 windows in. They don't want a whole bunch of different mix and match size windows. They don't, in a production environment, they don't want those. And so that's a key thing there. And then I think we were just sitting in a meeting earlier today where, we were talking about affordable housing. That's a buzzword that's going on in the industry, that everybody is concerned about the cost of housing. I think even today, yesterday, the interest rate went down. I think it went down a point, or I'm not sure. It went down a little bit. But the affordable housing argument is always out there. And so some of our builders are opting to use engineered lumber, let's say, on their custom homes, and they'll use dimensional lumber on their production line homes. And that's a way that they can put out a product that has a flat floor either way. It's just the cost of the inputs is less. Maybe the labor's less too in some regards, but maybe the material's more readily available. And it's a way that they can put out an equally quality product with just some less cost there. So
Right. So we'll see more what we call load path alignment. So we're seeing uniform height, uniformly located walls.
Yeah.
We're seeing the use of dimensional lumber. What I would say for more of our entry level or first time home buyer level homes, we're going to see a standard exterior header as a 2x material. So a 2x8, a 2x10, or the 2x10 on the first floor, 2x8 on the second floor. Because the 2x10, we're picking up floor load and roof load on the main floor, and then we're only picking up roof load on the second floor. And then if we have to go something bigger, we're going to a double 2x instead of actually going up to a full 4x dimensional lumber. And that's just a way of cost savings. It's nothing that's structurally inadequate. Everything is still structurally capable of holding that load. It's just we're cutting some costs versus going to just a standard oversized header. When we go into more of your mid-level, your second home, your medium custom, that's when we where we see a lot of our builders go to a standard 4x header. A 4x8 and a double 2x10. A double 2x10 actually holds slightly more load.
Nailed together with a little piece of plywood in the middle or something. That's what the old guys always told me. That's actually stronger.
Yeah. So it actually has a higher capacity because we get structural capacity with beams. It's more depth versus width. Okay. So the taller the wood member is, it's actually the equation that breadth versus depth. Depth is all depending on what material factor we're looking at. The depth is always raised to the second, third, or fourth power, which for the breadth, the width of the actual width of the member, it's always just multiplied by one. So you're depending on what element we're looking at, its shear capacity, its moment capacity, or its deflection, how it feels under your foot. That changes by the depth of the member much more significantly than the width of the member. That's how a double 2x10 actually has more capacity than a single 4x8. But there's also an appearance factor of it. So what we see is when we get into the mid-level custom is everybody just wants to use more dimensional lumber. They use those bigger, thicker headers. It's not necessarily structurally capacity different. It's more of a perception to it.
Yeah.
Okay? Yeah. And then when we get to our higher level builders, they actually aren't using any dimensional lumber in the headers. We're using glue lambs. And so what we have with some of our higher level builders is in the Northwest especially is a 3.5 by 7.5 or a 3.5 by 9 glue lamb is the standard. Okay. And the reason for that is that the level of the home or the level of the client. We're also typically in a first-time home buyer, we're going to see a lot more 2 foot, 3 foot, maybe 4 foot windows. And then maybe on a gable, like a front entry window, maybe we'll see a 5 or a 6 footer, right?
Right.
Possibly. Second-time home buyer, we're getting a little larger window openings. And then when we get into our mid-level custom or our high-level custom, that's when we get, mid-level custom, we're definitely going to be pretty regular.
Yeah,
5, 6 foot, 8 foot openings. And then the high level custom, the one that we just did one for the tour of homes in the Portland area. What was that? A 16 foot? I had a 16 foot opening. I had a couple of them, So that's where we're beefing up those headers to account for the fact that, and making that standard just for the sheer fact the design justifies it, the level of client justifies it, the custom home itself. So, but ways you can, again, value engineer a single 2x, a double 2x versus the dimensional. And then what we really try and do is we really try and keep with the standardization. So we specify a standard header across the board, something they can order in mass and possibly get a quantity discount on how much lumber they're ordering there. Then it also makes it easy for the framer because he knows I only need to look at the openings that specifically have a call out above them as anything that's different from the standard header.
Yeah.
So they can easily do that. So
when we intake a customer, we have them just for everyone's knowledge. When we take a new builder or even a one-off customer in, we have them fill out an intake form, which tells us all the different products if they already know what they want to use or what they're proposing to use. And so we can take that intake and make recommendations based off of that to either improve or stay in alignment with where their supply chain expectations are. And so that's the SOP that Royal's talking about, which is how we are able to get into alignment with our customers really quickly on what their expectations are from a material and wood design perspective. So
yeah, absolutely. And one of those SOPs are super important because every builder builds their home slightly different.
Yeah.
Right. They want to try and save money in certain places versus others, and almost every single one is different. And
they have opinions. They're people, and they know what they like. And so regardless of, let's say, their customer may be driving design, hey, I want 16-foot openings. The builder's saying, oh, well, I could use glue lambs or I could use 6x12s here. And what is my budget? I'm going to balance my budget against what I can use, what's going to perform best. And then, that's a conversation for maybe the builder and the engineer, what's going to perform the best over time, or what's not going to twist and crack and dry out and how it cause me drywall problems. Coming from the builder perspective, I believe, and you correct me if I'm wrong, glue lambs are more stable. They kiln dried most of the time, and they're glued layers that have been glued under pressure. and milled and planed and kiln dried. And so they're very stable. They can do much longer spans, but couldn't you also do the same span out of a 6x12, like a 16-foot span? Wouldn't that make it, or not? 8x12 maybe?
Yeah, I mean, it really depends on the loading. I mean, once we get into anything above about a 12 foot, you're typically out of a dimensional.
You are, okay, 12
Yeah,
foot. Okay.
Yeah, anything over about a 12 foot. And it's also access to the lumber itself. Finding a quality 6x12 that's 12 foot or longer, or longer than 12 foot gets questionable.
Yeah.
We just don't have the same grade of material that we used to have. Yeah. And which is important, from an engineering standpoint, that, our wood design code, it changes every few years, but the biggest thing that changes about it is actually the wood capacity, the strength capacity of the wood the wood that they're specifying, because they continuously test the material as it's coming out of the forest. And we're getting into shorter harvest times. A lot of the older growth stuff.
Second growth, right? Third growth.
Yeah. Yeah. You're not allowed to harvest it. There's restrictions on it. And so if you look at what we had for design values, even 10, 15 years ago of Doug fir or other materials versus what we have now, there's definitely a decrease in those capacities. Now that's where engineered lumber has really stepped up, which we're getting, we do get those higher capacity materials. There's multiple different types of engineered lumber. Glulam is probably the most common, but we're now seeing a significant increase in the use of what's called LSL or LVL.
Paralams, microlams.
Yep. And they're all different processes of how those are made. We'll have to get somebody from Weyerhaeuser or Boise Cascade on to talk about them, because there have been some innovations in the different engineered wood materials that a lot of people may not know about. We can bring those to light.
I know in the 90s I was framing houses and I was building my 2-story great rooms out of 2x8 or 2x6, and my more custom end builders started using in the 2000s like actual LVL studs in those walls, and they're straighter, longer, stronger, more lateral resistance, I would imagine. I saw a real influx of that in the early 2000s. All the houses were, at least on the higher end, were going to LVL studs even. I mean, talk about, not to digress for a moment, but your Shawwood series that you did on the Shawwood. I mean, every single stud is manufactured in there, right? They're not LVLs, but they're
basically a glulam that's then been milled down.
Every stud.
Yeah. Yeah. So it's pretty, I mean, that's pretty cool. So yeah. And we work with the higher end builders, or, you're typically not going to see a 20-foot tall great room, right? In an entry level home. You're going to see what you're going to typically see is either 7-foot ceilings or maybe an 8-foot ceiling on the main floor, 7-foot on the second floor.
Yeah.
And then those second homes, the common that you see is either a 9-8 or a 10-9, 10-9 combo. And so, but when we're getting into those taller studs, those taller walls or balloon framing, we absolutely start to look at getting away from dimensional lumber into like an LVL or LSL stud. And those are great products to be brought to the industry for us to work with. But it's different tiers of homes. So your entry level or your second home, you're typically going to see more vertical wall alignment to try and limit those studs.
Like stacking even on the inside.
Yeah.
For plumbing and everything.
Exactly. And we're going to continue that even into the underfloor, where we're going to align our cripple wall directly under what may be a mid-span interior bearing wall. So that way it's picking up our, what would be a typical span of our floor joists, along with the typical span of whatever our roof system is.
Trusses.
Into there. So, that's your pretty commonplace. And I mean, you see that in construction, even in these housing developments that were done in the 50s, 60s, and 70s, they all have a common mid-wall line, right? That hall, we've all seen it. You walk into the hallway wall, right? The hallway wall magically aligns with the ridge of the roof above. And then if you go in the crawl space, there's a strip footing with a cripple wall underneath it. And that's just a mid-span support, fully aligned vertically.
Yeah, and there's a lot of that plumbing alignment too. It seems like in some of there's I don't know if you call them wet walls or whatever, but the walls that house all the plumbing and the plumbing vents, the water lines, it seems like those were all stacked and aligned with good mindful thinking on where bathrooms were going to be, or washrooms, or utility rooms. Those things now are a little more fragmented in design because of the introduction of PEX and the flexibility with plumbing and all of that that's kind of happened over the last 20 years. But in those older homes, there was a lot of wet walls that were lined up as well. And they still stack in apartments, those types of things in apartments all align, of course. But
the use of PEX, and we're seeing definitely a bigger shift to PEX from the older copper and CPVC piping. PEX is just very resilient, very forgiving, and those aspects.
Easy to put in.
Yeah. Here's an interesting fact. So during the World Wars, there was such a pullback and need for metals for use in munition that we actually had to build homes differently. And that's why you see a lot of homes that were built in the World War II era. They all have their bathrooms will all be along one wall side, and the opposite house on the lot next to it will be on the same common wall side. And that was to reduce the use of the cast iron and copper and brass that they were using to run the plumbing into the house. They completely changed how they design homes just to try and reduce materials by that little bit. So
yeah, the good old cast iron vent, like the giant 6-inch stack that weighs like 30,000 pounds in the center of the house. And I don't know about you, I'm a little bit older, so I've renovated a couple houses. And as soon as you get to have to remove that stack, or there's something you have to do around it, it's like this giant pain in the butt. So those things are very heavy back in the day.
We had a very high level builder. I mean, I'm going to say he's very high level. I was very unfortunate. I was very sad to hear. I think he said he's built his last home and now he's focusing on another project altogether. But his home's part of the spec was the drain line was cast iron. Oh, wow. And I said, well, why are you doing that? And he goes, because then you can't hear the water drain. Yeah. He goes, he did it purposely because his clients were so high level. He just immediately was like, hey, if somebody's in a downstairs bedroom that's on a common plumbing wall, they are not going to want to hear water coming down the pipe. So he took the extra expense and the extra effort to make those drain lines all cast iron. Yeah. I mean, it is. I mean, in today's day and age, it is very much an extra expense and extra effort.
They don't do that anymore unless it's custom spec for sure.
Yeah, absolutely. So you're going to see the vertical alignment in those. And then as we get into the mid-level custom or the higher end custom, mid-level custom, what I call mid-level custom is basically the home is custom until about the top plate, right? And then that top plate up, it's all the engineered trusses. And one house in particular that I'm remembering, I went up to it. I thought it was a very cool, very fancy custom house. And come to find out, the entire second story was all built into the trusses. So it was literally that you had a block out for where the stairs came up, and everything else about the entire second floor was all in the trusses. Yeah.
That's common over like a garage, like a bonus room thing.
Yeah, that is. Well, bonus room, or I like to call them a frog front room over garage. Yeah. So those. Yeah, nice. Yeah, the use of trusses as an entire floor system, where you're literally combining the roof and the floor, is a very cost-effective way to do it. But again, you're using a dimensional lumber. You're optimizing or maximizing the span of those systems as far as they can be. You're taking all of the material increases because it's built in a manufactured environment. it works. That doesn't mean necessarily it's ideal. I was brought in on a construction defect case once where they did the floor trusses, or they built an entire portion of the second floor into the roof truss system. Mm-hmm. And the home wasn't that old, and the floor tiles were popping. And it was because a couple things. One, the dimensional lumber was drying, and that dimensional lumber was part of the trusses. So everything was shrinking. Yeah. And because they had taken all of the optimization for that material for the structural capacity, the deflection was actually higher than what it really should be. And the person that designed the trusses just accounted for basic loading, didn't account for the fact that it was going to necessarily have a heavy floor of a high-end tile and all of that materials, plus all of it was in a bedroom, all of the bedroom furniture and everything else that went along with it. And so that was what we determined was it was a situation of structurally based on the trusses and stuff, it worked, but the level of construction, the quality of that construction probably should have been something a little more stick framed as far as what the end client expected, as far as where the interior finishes.
So that is a perfect example of where you could create your room inside of a truss. You could have it cost less in the short term, right? But then in the long term, it was a bad decision.
Correct.
Based on things that should have been expected, i.e. heavy finishes, static loads that were going to sit a bunch of furniture, and none of that was really taken into consideration.
Right.
It was just done to the bare minimum.
Right. And that's where, there's a line with value engineering, right? It's always interesting to me, and you probably noticed it when you framed, is people seem to not care about everything that's actually holding their home together. They don't even feel like it's a home until you get sheetrock on the walls. And then they're like, oh, look at this. Now it's starting to come together. Not realizing that everything that month, 6 weeks, 8 weeks, whatever it was for the foundation and the framing is everything that's holding all of those finishes.
Right? I mean, I don't know how many times we've had this conversation, and maybe this might even be an entire podcast worth of conversation on this one, but I'm going to say what Royal said in a couple of different words, that the dirt work, the earth prep, the foundation, the framing, those are the things that you cannot cut corners on. Those are the structural elements of the house that if you cut corners on, or you do improper value engineering per his trust example, is that you will have problems down the road. And that's what we mitigate as a structural engineering firm, is we put our best foot forward into giving people the best possible outcome by knowing and being experts in that field to be able to say, no, you can't cut corners structurally. Do not cut corners on your earthwork prep. Do not cut corners on your foundation. We could go into a current example. We will not do that. Do not continue to pay your framers as if it's 1985.
Right.
Because they're going to cut corners. And I mean, how frustrated I am in the industry, that's a whole political conversation, but there's a lot of things going on within the industry that where people are cutting their costs that you want to be careful of.
Yeah.
And the structural portion of it is not where you want to do that at all.
Well, yeah. And another, again, foundation retrofitting, right?
Yeah.
So in a typical, say a 2,000 square foot, 2-story home, the amount of concrete in that entire foundation is somewhere between maybe 5 to 9 yards total.
Yeah.
Somewhere in there. Okay. So let's say it's 9 yards on the top end, or let's say it's 10 yards. Okay. The average cost in situ. So this is the yardage, the formwork, the everything, all of the hardware for that foundation to be put in situ is running about $500 a yard.
Yeah. Call it 10 yards just for the ease of the math.
Right. So $5,000 total for that entire foundation.
For material.
For that foundation to be fully formed and poured and all the hardware placed in it. Okay. Mm-hmm. That's for the entire foundation for the whole house. A retrofit pier, so a deep foundation helical pier, the in situ cost for a foundation retrofit company for just one pier on average is $3,500 per pier.
Per pier.
Per pier. And you're replacing those piers every 6 to 8 feet on center around a home.
Yeah.
So I've had to pier entire houses that were only 2,000, 2,400 square feet that we were well over, we were 10 to 15 piers to retrofit the foundation. So think about that. You cut maybe $1,000 here, $1,000 there. The retrofit is far, far more expensive on structural items than anything else.
Yeah, and so essentially a house is spread across its footings and its stem wall, and so if it starts to sink, crack, shear, and the earthwork is not done right, then a company goes in and they drill down to find good dirt, and then they fill that, they jack your house up, right, and then they fill that with concrete, and then they set it back down on those piers. Is my thinking right in this way? Is that close?
There's different kinds of pier systems. We'll do an entire other show on it, but basically they're driven into the ground to hit something solid. To then support the house.
Yeah, because the whole thing sits back down on it, right?
Correct.
Yeah.
Yep.
And so you spend $50,000 for that minimum.
Right. Oh yeah, easily.
Yeah. Not to mention all of the interior damage from shorting on your foundation or shorting on your dirt work, or not paying for the proper value engineering, or putting the right kind of lumber in the right location. Right.
There's a line of where you value engineer. When it comes to soil prep or the foundation, put that extra inch or two of gravel on the ground.
Yeah. Compact it more than you should.
Compact it better.
Yeah.
Do that extra,
get it tested by a geotech. Don't think, I'm going to save $1,000. I'm not going to have my geotech back out to check, that I got my 1,500 PSI per square inch or whatever it is. Just spend the money for the geotech.
Yeah, exactly. I mean, it is. And so many people try and skimp on that. I mean, we do work in states where flat out a geotech report is required on every site or every development. It is required on every development. I don't know of a single state that doesn't require a geotech report on every development. But it's when you get into individual home sites outside a development area that it gets questionable. Yeah. And then the same thing with the foundation is, foundations, concrete placement. We just do what is necessary. We're not doing overkill. But the fact of the matter is we see people skimping on the quality of the concrete they're doing, cutting down the rebar that they need, cutting down on the hardware that they place. I worked on one house that was almost 8,000 square feet, and I went in to inspect it because the framers had framed the entire house. It was 3 stories, and they said when they were up framing the 3rd floor, the home was drifting. And I came in and I inspected it, and they hadn't put a single hold down in the entire foundation. They didn't place a single one. They didn't. And I was like, where's all your hold downs? They're like, well, we didn't know we were supposed to do those. I'm like, they're on the plans. They're in the engineering. They didn't have a single hold down, a single strapping, a single anything. And it was too far beyond to be able to retrofit. And unfortunately, the homeowner ended up losing the entire house. And it was because their people were cutting the corners. So there's places where you value engineer and there's places where you don't. So, and then if you're getting into high-end custom, we're going to be doing things a lot, like I said, a lot higher end. So we're typically not going to be using any dimensional lumber. Your floor joists are going to be engineered trusses, engineered floor trusses, or truss joists, a silent floor system. Your headers are going to be glulam material. We're seeing longer spans, bigger openings, everything like that. So we have to use that engineered timber, or then we're even getting into steel. We just did one house where I had a whole steel brace frame, and then we had a massive garage area that was supporting 3 floors above. And we had a large steel beam that was actually on concrete columns. Those concrete columns were coordinated with the architect. They wanted it for an aesthetic, but those are the levels that you're going to get into, and it's good to there's different tiers to it. So sure. Now laterally, we've talked a lot about lateral loading because vertical loading is, like I said, that's your gravity loads. That's just what it's holding up every day, all day with no matter what. Lateral loading is basically what that building has to resist when things are bad. That's the easiest way I can put it. You have exposure. You have a heavy windstorm. You have a seismic event. You have a natural event like a hurricane or a tornado. That's when we're designing the lateral load. And one of the biggest things, the biggest events that brought about better consideration for lateral loading, we always knew about wind loading, right? Yeah. Wind loading was something we always considered. It's just become something definitely more measured and calibrated over the years. Seismic loading really didn't come into discussion until the major earthquake, the Loma Prieta earthquake in San Francisco.
Well,
yeah, and in which we had a lot of buildings collapse. Predominantly, the buildings that were collapsing were not wood construction. Wood construction, again, very flexible, very malleable. It flexed with everything. But this is why you see when there's seismic events in other countries, a lot of buildings collapse because their main building material is with concrete or brick type material, which doesn't it's flex.
Rigid. There's no
rigid.
Yeah.
So when that occurs, you get collapse. So that's really what brought forth the seismic design code into the United States, and everything is really stemmed from that. There's not a single. I've been to a lot of seismic tables, a lot of seismic test labs. And the first seismic event they always run equipment through or build through is the Loma Prieta. It's been mapped and used so many times, they've got it built into these programs where they go, okay, we built a wall assembly, we've got a column, we built a mock-up house, and they run it through. They literally run that thing through the Loma Prieta earthquake and see how it handles it. And so, but your lateral loads, right, your wind events, your seismic events, tornadoes, stuff like that, which tornadoes are high wind with impact, hurricanes, high wind with water with impact. And there's multiple different ways to design for lateral, but no matter, in the long story short, there's prescriptive path, which provides a multitude of different options. But really, as we're seeing wind loading increase, seismic loading be considered greater, and then we're seeing a decrease in the wood capacities. We're seeing more and more builders and more jurisdictions realize that, yes, we've got this prescriptive path, but the prescriptive path has gotten so conservative, it's no longer cost effective. And it's actually more cost effective for me to have an engineer my houses for lateral than it is for me to just try and have my designs either conform with prescriptive, or the common one we get is, hey, I tried to design this to prescriptive, but the code's changed. It no longer meets prescriptive. Now I need it engineered, and I need it right away because this home is supposed to break ground next week, right? So
yeah. Coming from the builder side, it has been the prescriptive path with a customer that has, for some reason, decided that they have to use this prescriptive path. The tables from the jurisdiction, you don't need structural engineering. It is engineering, but it is a method by which you can use to do it yourself. It's a DIY, is what it is. And so I don't know how many times I turned plans in with prescriptive path methodology, and it came back to me 4 or 5 times through the jurisdiction. It took months of trying to get those things passed because the plans examiner themselves don't have a great deal of confidence or know it very well. And so there was just questions after questions on it. And now it sounds like, from what you're saying, it's gotten so convoluted that they've made it so complex that it's actually less efficient, which is what the initial goal of the whole thing was in the beginning, was a simple structure. If you want to go build a shed in the back of your house or add a garage or something like that, you should be able to use the prescriptive path and just do that and not have to get a bunch of additional cost. But all the red tape and everything that's happened throughout all of those prescriptive path tables now makes it less cost effective. You might as well contact an engineer to do it. And I tell you, just from a time perspective, you might as well do it because it costs me months in design or in permit review.
Oh yeah, yeah. Well, and you know, especially if you're submitting for a permit and then that jurisdiction charges you for an additional review fee or anything like that.
Yeah.
Yeah, I think it might have been you when you were working for one of the builders and you and I met. Your mantra was prescriptive doesn't pay, because you were paying your home designers to then design to this prescriptive path.
Yeah.
To then have arguments and back and forth with the jurisdiction
for months. 99 in 1 month. I had 99 plan review letters on like 30 plan submittals. So 3 times on average for each plan in a 1 month period. And I said, no, we're done. We're done with this. It's out. And that's, right. I think that's when we called you.
Yeah. Yeah, it is. Yeah, we came in and
this was 15 years ago, I think, by the way, people.
Yeah. It's been a while. It's been a while that you and I have been working together.
Yeah.
But I mean, what we did, I can tell you this year, we've done around 1,500 doors. Mm-hmm. I think we've gotten maybe 10 plan review letters.
Not a lot.
Almost, I think all of those, or almost all of those, were from the exact same state.
Yeah. The same review department, probably.
Yeah. I'll say just the same state. I think there were different.
Not naming names.
Yeah. Arizona. But yeah, they were all from the same state. There was, just them almost enforcing their own standards on stuff. But for most of like Oregon, Washington, California, stuff like that, when it comes to the engineering side of the stuff, everything flew on through California, and they got their own things that they always seem to hiccup on. With the engineered versus prescriptive path, we definitely see a lot fewer plan review letters, a lot easier acceptance. There's just better pathways to it. But when we're engineering it, try not to insult my industry too much, but we have a lot of people that have been engineering homes for a very long time, and they have a way that they engineer them, and they don't want to change. If you really, really study the wood design code and you really understand the codes, and if you understand prescriptive path as well, you can engineer even some of the largest, most complex homes in a very simplistic fashion with conventional methods. But you have to optimize your shear wall paths. You have to use aspects of the code to their full ability, because again, we're working with wood. Wood is flexible. We're not working with like brick and concrete with the rigid systems. So there's parts of the code and there's things that have developed over, I would say, the last 10 to 15 years that, if not even 20 years, that the vast majority of engineers have not integrated into their systems and processes. One of the builders we were meeting with actually earlier today was talking about he's using us and he's using 2 other engineers for their workload and looking to go exclusively to us just because the other engineers they've been doing a long time. I think one of their engineers, he's in his 70s or something, and a little more conservative and not wanting to or willing to learn new systems or processes or additional design methods. And, it's helpful in my aspect. And this is one of the reasons I actually love having you as part of the team, is because you probably talk to our engineers as much as I do, because you're talking to them about constructability and efficiency and like, hey, you guys looked at it and you engineered it this way, but really how they're going to want to build it in the field, or knowing costs, we're going to want to do these things instead. Is there a way we can make this the key shear wall instead of this one the key shear wall? And so again, from the lateral side of it, we have an SOP set up where it's an order of operations kind of situation of what walls within a home we look at to be our shear walls.
Sure.
And we know we've learned this and we've established this deductiveness to it based on input from our builders of what way costs more versus the other. And so we've input that value engineering into our systems and processes to make sure that it is that way. So with that, how we look at our value engineering for the lateral systems is the exterior walls, for the most part, in most of the states that we work in, are always sheathed. So if they're always going to have sheathing on them, make them a shear wall. That way we're already optimizing the sheathing, the plywood, whatever they're going to have as the siding backer to its full capacity. And when we're doing that, there's 4 different types of shear wall systems, but we'll talk about those. But your exterior walls are always what's optimized first, and then the back or your garage walls. And the reason we look at optimizing those next is they already have a foundation under them.
Sure.
We're not having to add concrete under those walls. It's already there for us to work with. So let's use those. And then we're looking at stairwells. Our stairwells coming down. The reason being is stairwell walls are always bearing. They're supporting the load of the stairwells. So we use those walls next.
And, yeah. The floor above, yeah.
Right? Because we have what's great with them, we always have a continuous load path, right?
Yeah.
Most stairwells in most houses are aligned. They're aligned between the floors. And so if it gives us that, we have a continuous shear wall line all the way through. And then lastly would then be any other kind of interior shear wall line, because those are going to be the most costly and the most complex.
So from a builder standpoint, this is where you get into, okay, if there is a mid-span wall, let's say on a long exterior wall, a 40-foot long rear wall, and you have another perpendicular wall, 10 feet, because there's a 10-foot bedroom on one side and 30 feet of great room and, living room and kitchen on the other side, making that a shear wall to laterally brace that 40-foot back wall. I've also seen sheetrock with a certain screw pattern. What do they call those? One of the builders use those almost exclusively. Shoot, I forget the name of those, but they use actually the sheetrock for interior shear. And that creates some of that interior, actually sheathing the interior walls with actual like OSB or CDX can create problems and jam extensions and things like that at doorways and trim issues. Doing it with the sheetrock's less so, but then it costs in building time and inspections, because they have to inspect that sheetrock before it can be mudded and taped. And then, so I'm saying, how does that coalesce with your 4 different types of exterior sheathing, being able to achieve this lateral means that you need to achieve, but then also balancing value engineering, not having to do those interior shear walls if you don't have to, meaning sheeting interior walls or doing brace panel walls, BPs, brace panel walls with the drywall.
So here's a newer development, and it's something that's changed in the code as of pretty recent, is we no longer can consider sheetrock for seismic resistance
anymore. Is that just the last iteration of it that it changed? Or okay.
Yeah. So we cannot use sheetrock for seismic resistance whatsoever. So what we typically do, and you've seen we use a 3D modeling program, and we're able to build wall sections. Every wall section, we're able to specify the exterior sheathing, the types of nails being used, the edge and field nailing, the size of studs, the spacing of the studs, and what the interior finish is as well, whether that's sheetrock or we're looking at a double-sided shear wall then with sheetrock on top of it.
Right.
Well, what's been required now with what we call it the SPIDWIZ, but from the American Wood Council, is we now have to ignore the strength contribution or the shear contribution of the sheetrock when we're designing for seismic. Because when we analyze a wall section for lateral, we have to analyze it for wind and we have to analyze it for seismic, and we have to take the worst case scenario.
So you're automatically looking at seismic, that discounts wind.
What we have seen as of recent, again, this is with the ASCE 7, the actual applied forces, when we're determining the applied forces, is we've seen an increase in seismic loading and how much load we actually have to consider, what percentage of the load is in what's called an MCE, maximum considered earthquake. And so we've seen an increase in that, but then we've seen a reduction in the actual resistance forces of our wall assemblies themselves. So
the material, the actual strength of the material.
Right. So as a result, what we've actually seen in residential design is we're seeing now where when we analyze it for wind and seismic, it used to be for basically any 2-story house, wind controlled all the way down.
Oh,
and
really?
Now,
okay.
Yeah. And now we're seeing situations, because understand, it's not the entire house, right? If I look at the house and it's not a situation of Oh, seismic controls for the entire house or wind controls for the entire house. It's literally every single wall line that you're using as
every facet, every
yeah,
side.
yeah, every side, what we call an FRE, a force resisting element.
Gotcha.
Every shear wall line we have to analyze as wind and seismic and determine which one is greater, which one's imposing the greater force, and then design that. And then that's the one that controls, and we have to specify our sheathing and our nailing and everything based on that. What we do to optimize or value engineer is we do build those wall sections in our modeling software. When wind does control, we do use the additional provided capacity of the sheetrock, which typically is only about what's called 60 pounds per lineal foot of shear, which doesn't seem like much, but
add it up.
When you add it up, it helps. And then when we're talking about the transition from nailing at 3 and 12 versus a nailing on 2 at 12, there is a significant cost savings in there, because when we get to nailing at 2 and 12, you're required to use 4x edge members, not just your conventional 2x studs.
Yeah.
And so your blocking gets beefier, your framing gets beefier. That's a significant added expense. So having foresight into that to account for it is very important. Now, the other aspect of it is knowing and appropriately using the 4 different conventional framing methods. Okay.
Right.
So there's what's called segmented, and segmented is what most engineers know, use, and they kind of just stay with it.
Is that the areas between the windows?
That's the areas between the windows. And that would be as a prescriptive comparison. If a builder is used to prescriptive terminology, that would be either a WSP or an ABP, meaning a wood shear panel or alternate brace panel, in which it's sheathed and then there's a hold down at each end. Okay. And there's no openings. There's no openings in between. Okay. The next one up, and what we use probably more than any other system, is a perforated shear wall, in which we're designing, considering the sheathing that's not only between the openings, but above and below the openings. And then we have to take a reduction in capacity for the fact that there is an opening.
Sure.
Okay. So again, commonality with prescriptive would be what's called a CSWSP, or a continuously sheathed wood structural panel. Okay. Then our next step from there is what's called an FTAO, okay, which stands for force transfer around opening. In an FTAO,
is that the straps?
That's the straps. So you run straps above and below the window opening. You can't do an FTAO on a door. You can do them around windows. And there's guidelines on how much wall I have to have on either side of that window opening in order for it to qualify. There's these different guidelines, but it's a situation of, I may have a situation because what it does, what an FTAO does is, if I have say a 10-foot tall wall, okay, and I have a 5-foot tall window, when I now put those straps in, when I analyze for my overturning, which is what dictates my hold down sizes, I actually now don't take the full height of the wall. I take the height between the straps, or the height of the window.
Oh.
So my overturning is now only multiplied by 5 instead of by 10.
Sure.
Which in the case of hold downs, okay, and the hold downs have anchors that go into the concrete. If we're looking at a hold down that may be like what's called an HDU 11 or an HDU 14, HDU 14 being a very large hold down. Well, for a contractor, the anchor bolt for an HDU 14 or even an HDU 11 is not retrofittable, meaning if they place it incorrectly, the only fix is to take out the concrete and re-pour it.
Yeah, you can't drill and epoxy that baby.
Correct. There's no epoxy retrofit available for that. There's too much forces being put into it. If I look at it and I say, oh, well, this works as a perforated shear wall, but it puts me into a situation of I've got an F hold, or I'm using our nomenclature. I'm getting into something that requires a 1-inch specialized anchor bolt or something in there. I've really put my contractor in a bind if the situation is that their contractor installs it incorrectly.
There's no flexibility.
All right. So what we do is we design it as an FTAO. Yes, they have to put some straps above and below the window, but that may take us from requiring like an HDU 14 or an HDU 11, which have a 1-inch anchor bolt system,
Like a 5 or something. Yeah.
into a 4 or a 5, which has a more common 5/8.
5/8.
And if they do place it incorrectly, no big deal. We drill the concrete, we epoxy in an anchor, we move on with life. Those are your 3 most common in walls with opening, or wall segments or walls with openings. And then the last one would be a portal frame. And with the portal frames, it's exactly that. There's a single leg portal frame or a double leg portal frame. These are most commonly used around garages. However, we have used them in what I would call more entry level houses. We're doing like we've got narrow construction, and they wanted like a nice large slider door in the back.
Yeah.
We have specified portal frames around those slider doors just because we had nowhere else to put the shear. So we see as an error from some people in our industry is they gear towards more just these segmented shear walls, which winds up with way more hold downs than what is necessary. They don't optimize the use of the exterior shear walls and start using interior shear wall lines, which adds additional expensive sheathing and hold downs in interior wall lines. They don't consider the use of an FTAO or the creative use of maybe a portal frame in areas where there is a situation of there's a large opening or needing high force resistance in different areas. And those are your 4 main conventional engineering methods. There is one that I will touch on just because we're seeing it a lot more in our track home, our narrow construction. I mean, shoot, we just did a townhouse complex that the units were 17 foot wide and they were 3 stories tall.
Yeah.
Right. And then you got not giving me a lot of wall to work with on the front and back of that place. Their most common engineered system company is called Simpson, and Simpson has strong wall systems. They have a wood strong wall and a steel strong wall system. And those things have a great amount of capacity associated with them. And those see, a portal frame, we're restricted to 16 inches wide. That's as narrow as we can take them.
Right.
Now, I'm sure I've got some framers that are going to go, what are you talking about? A portal frame's 22.5. Yes, portal frame, most commonly up until a couple code cycles ago, 22.5 was the common. Now with new testing from the APA, I think it's called the T1000 is actually their report on it, we have a portal frame system we can go all the way down to 16 inches on. That's very helpful. And then we also have what's called a single leg portal frame, where it's only on one side. We connect to the header over the top, and then it's a singular hold down on the opposite side, which allows us to put in a 12-foot or 16-foot garage wall with only one singular wing wall. That narrow construction still allows us to use very conventional methods. But the higher strength system is the Simpson Strong Wall, and we're able to go to a 12-inch wide wall on that. And so we actually just did it was a townhouse complex, and it was 3 stories. It was super narrow, and it was in an area that was high wind and high seismic. And what was cool with the Simpson Strong Wall system is the forces were so high, we actually had to specify a double strong wall. So we actually put them back to back on each other.
Oh, wow.
So, and that actually matched the wall framing depth, but we put them back to back on each other. It's using those things available to us in creative ways to stay out of, because the only alternate that would have been for us, instead of doing that double backed or that back to back strong wall, would have been going to a steel brace frame system.
Is that a 2-car garage you're trying to fit in a 17-foot unit?
Basically, yeah.
So a 16-foot door.
Yeah.
In like a 7, or maybe a cheater, a 15-foot door and a 17-foot
opening
house would only give you a foot on each side. So,
yeah. So we did a double-sided, so back-to-back Simpson strong wall on there, and we were able to meet the loading capacities. But again, it's just using the materials that are creative to you and available to you. One other system that I'll bring up, because we've specified it in some higher end homes that have the long, like large openings. We have discontinuous shear walls and stuff like that. There's another product from Simpson that's really cool, and it's called an MPBZ. Not something you want to say 3 times fast.
It's quite the acronym from the
Right.
Army Man. Loving it over there.
Yeah, I'm not calling for any of those over the radio. So yeah, it's a moment post base. So it's a moment resisting post base, which means if I have a floor diaphragm or a roof diaphragm that's resisting or transferring wind or seismic loading, but let's say I don't have a good shear wall anywhere around for me to tie that into.
Sure.
But I've got my wood framing, I've got my glue lambs, and I've got a column coming down. I can now use this MPBZ, which is actually a fairly new product from them, to make my column a force resisting element, because I can determine what my force is going into the top, what my lateral forces are going into the top of the column, what the moment is at the base of the column. And now I have a moment resisting base out of a wood column. Again, these situations used to force us into steel, and then you're having custom steel fabrication and all that added expense and effort. We're now able to make it work with just wood, which is awesome.
Wow. The optimization, performance, flexibility, structural integrity, sustainability, all the illitidities, all these things, the ittities with wood just offers a great deal of flexibility, I guess. And, you know, designing.
Another illity.
Yes. Designing with wood just has all these illities. So we'll leave you with that. No,
and we have disabilities. All right.
Coming through right now. So, but no, I mean, I always learn something new when talking with you, Royal. And I think that another thing that just comes to mind from the builder side is and this is not a plug for PLIRIS, but it's mostly just what a need a builder has to have a good value engineering minded engineer in their pocket, whether it's PLIRIS or whoever else that builder uses, how important that conversation is, starting from the beginning of our podcast about the foundation, the framing, and the earthwork, how important that is, but how detailed it actually is sometimes to make some of these things work. And it can cost you a great deal if you make some decisions that are not in your best interest. Someone else is making these decisions. So having someone that you know and trust as your engineer and working through the value engineering process is so important, you know. And that paired with the wood aspect of the flexibility and design and optimization and really the sustainability of wood construction and all of that, just paired that all together. And I think there's a lot there and a lot to know.
The introduction of the Simpson has been a great advancement in our wood construction. They've
out in the field, we called it the Simpson insurance, and we weren't necessarily that open to it in the beginning because it was like, oh God, they're making us, nail all of these metal brackets on everywhere now. Like, what is this? Like, come on, bureaucracy. Like, what's going on?
Right.
But,
there are good parts to it. There are bad parts to it. I started and I had exposure with engineering of homes at a very young age. And my grandpa always joked about it. He's like, I was engineering homes before Simpson was invented. There are benefits to it, but unfortunately what we've seen is a lot of the industry go to, well, we're just going to slap brackets on that. We're going to slap hardware on that. We're going to do this over there. Why would I use a piece of hardware that it takes 10 nails to nail on that I've got to, go to the store and buy, when it's forces that a couple of nails or a structural screw resists? Like you said, it's the Simpson insurance of like, hey, well, I don't know what goes there, so I'll put this bracket on there and we'll call it good. Sometimes it gets excessive, and especially when you're trying to keep the cost of construction down for these entry-level homes, the excessive amount of hardware gets up there. We've had a couple builders that had engineers do their homes that, like I said, they were very old-time engineers, use certain systems where we then re-engineered their homes to give them a comparison to it. And the amount of hardware and sheathing that we were able to save them was more than what our engineering fee was to engineer the home.
Yeah.
So we paid for ourselves and then some.
That's a fact. That's not a plug for PLIRIS. That's just
Right.
a fact of if you keep up and you know what's going on within the industry and you're thoughtful about your design and how the structural things are reciprocal with one another and the products that you're putting into the house, and you're consciously thinking about all of those things and not just, you know, rinsing and repeating and not paying attention, what a big difference that makes.
Yeah, it is. It is huge. It is huge. And I mean, we try and be aware of that and mindful of it. And it's always great when you know that you're being of value to your end client.
Yeah.
And, you know, in that situation, I mean, that's the best compliment I've ever gotten is, you save me more than what you cost. Perfect.
Yeah.
I hope I save you 10 times more than what I cost you.
Yeah.
That's the whole point of it. So, but anyways, I hope this was helpful. I hope this was educational. You got some insight into the different systems. If you are a home builder and called out your engineer or being the old timer, I apologize, but I want to bring up, you know, it's good to learn the new things. Things change, design changes, products come out. It's great to stay up on those materials, those advancements as they come about and implement them, because innovation helps save money. It's supposed to save money and save time. Otherwise, nobody would adopt it. So
yeah, and value engineering is not cost cutting. It's, you know, it's performance optimization is what it is. So
exactly. So awesome. Do you have anything else, sir?
No, I just want to thank everybody for their time. Please follow us on social media. Hit the like button. We want to keep doing this. We want to bring guests in. So if you're interested in being on the show, please hit us up on any of the different social media platforms, and we'd be happy to chat with you. And we're just looking forward to doing more of these, and we'll see you next Friday.
All right. Beautiful.
See ya.
Have a great day.